We now know that the limit when x goes to 0 of sine x over x is 1. And it turns out that this is very useful to find out the limit of something else involving not a sine but a cosine. So let's try to do that. We can use this result to show something else. This limit here. This limit is another one that you'll be able to use throughout Physics 111, and together they can be very useful for demonstrations. They will come out specifically when we derive the rules of differentiation from first principles, and to understand, for example, how the derivatives of sine x and cos x are related between themselves, sometimes with a minus sign, which you probably already know. But how can we show that this is the case, and why do we need this? The goal is to try to calculate this limit. If you try to calculate this limit and go through the list, you first can sub in, and you'll see that you end up with 0 over 0. That's no good. It's undefined. If number 1 doesn't work, there's a series of things you should try, and it turns out that calculating this limit is a very nice demonstration of how the different techniques actually should be put together to then re-express it into something that we can calculate. You can also find the full derivation at the very end of section 3 in the lecture notes. The first thing we're going to do is multiply and divide by the conjugate. Multiplying and dividing by the conjugate, in this case the conjugate is cos x plus 1. This means we can further simplify this, and again, don't do anything to the terms on the bottom as usual. What we can do now is to use the fundamental trigonometric identity that tells us that cos square x plus sine square x equals 1, which also means that cos square x minus 1 is equal to minus sine x. So cos square x minus 1 is minus sine square x. So this is what we're going to use. Once you get to this step, all you have to do is remember properties of limits. So we're going to split it up with the product property, quotient property, and the fact that if you're multiplying with a minus, you can always take that minus out. So the first thing we can do is we take the minus out. We split up sine x over x. So this is the limit when x goes to 0 of sine x over x times the limit when x goes to 0 of sine x. So we've got rid of x and this term, and then times the limit when x goes to 0 of 1 over cos x plus 1. The great news is that we can calculate all of these, and therefore the properties of limits do apply. So remember that this is only true if the individual limits exist. In this case they do. This one is 1. We've showed it before. This one is particularly easy. We just plug it in. That's 0. And this one, you plug it in and you get 1 over 1 plus 1. That's 1.5. Because you're multiplying by 0, you get 0. So we've proven that the limit when x goes to 0 of cos x minus 1 over x is 0. And I think this is a really nice demonstration of how things can build on things you've demonstrated before, how to multiply and divide by the conjugate, and then also how to re-express your limit in terms of things you know. And in this case, you've checked, or you should check, that all limits exist, they're real numbers, and therefore you can really use the properties of limits. If you got to this stage and you didn't skip things, then you should be ready to go into differentiation. And we're going to be using limits to define what a derivative is from first principles, and then to demonstrate derivation rules that maybe you're already using, but is key to put down with mathematical rigor. And some of these techniques will actually come back all the time, especially for like the product rule or the quotient rule. The derivations involve understanding the properties of limits.